Okay, so this is the information about marginal and conditional distributions. Let's go ahead and finish filling in this chart here. We got 18, so what is this here? 23. Okay. So this is considered a margin because this is the totals in one of our margins. Okay? This is also considered a margin here because this is the totals. Okay, so these would be what totals over here. This margin on the right-hand side would be the gender totals. So I can tell in this class I have 6 males and 17 females. And then over here on the bottom, what would this be? My political margin, because I can tell how many in each particular, the totals in each category. Okay, so let's answer our question. What percent, so let's do relative frequency, what percent of the entire class are girls that have liberal political views? So what would that be? Girls with liberal political views out of the total class? Correct, 2 out of 23. Okay, so let's figure out what that percentage is. Okay, so that would be our 8.7%. And I'm just going to do 1 decimal on these. All right. What percent of the liberals are girls? Correct. 2 out of 2. So that would be 100% of the liberals are girls. Okay. What percent of the girls are liberals? What percent of the girls? So that would be 2 out of 17. Because of the girls, that's your total on the bottom. Yeah, tricky. Okay, so that would be 11.8%. All right. What is the marginal distribution by gender? So here's how you do that. Again, you're going to get that from our margin that is about genders. Okay, so let's figure out our male marginal distribution. What would that be? 6 males out of 23 total. So that would be 6 out of 23. So therefore our male distribution would be 26.1%. Okay. Our female distribution would be what? Marginal distribution would be, yes, 17 out of 23. Okay. So that should be the rest. I should be able to just subtract, 100, take that percent from 100% and get the rest. So that would be my 73.9%. And what do those 2% total up together? 100%, and they should. Okay, so now let's get the marginal distribution for the political views. Okay, so what am I going to figure out first? Liberal. So liberal would be what? 2 out of 23. Very good. And so what's that? We've done that, 8.7. Yep. Okay. Okay. Moderate would be my what? 16 out of 23. Okay. And so that would be 69.6%. Okay. And so now our conservative is going to be the rest. So I could add those together, and so 8.7 plus 69.6 is 78.3%, and then I'm going to subtract that from 100%. So I got 21.7%. All right. Questions there on marginal distribution. So we just got those from our margins. Make sure you are careful. Remember, these first 3 questions were kind of tricky. Make sure you're careful on what you're comparing it to. Of the class, of the liberals, of the girls. Okay. Next section is on conditional distribution. Okay. A conditional distribution does not come straight from the margins. That is a particular, condition based on another condition happening, a particular event. For example, let's find the conditional distribution of, let's find your political preference conditional on the fact that you are a male. Okay, so how do we do that? So that means of the males, how many of them were liberal? So what do we say? Of them, 0. 0, so that would be what? 0 out of 6, okay, so 0%. Of the males, how many of them were moderate? 6 out of 6, so that made it 100%. I'm going ahead and putting the relative frequency in there. Of the males, conditional upon being a male, how many of them were conservative? 0, right, okay. So we did have our total of 100% because of our 6 people. Okay, got it? Conditional upon being a female, how many of them were liberals? 2 out of, it was 16, right? Oh, we got 17. Okay, sorry. 2 out of 17. And what percent does that give us? Okay. I'm going ahead and putting that relative frequency. How many of the females were moderate? 10, and then 5. So 10 out of 17 were moderate, and 5 out of 17 were conservative. Okay, so let's do those percentages. .8%, and this one's 29.4. Okay, that works out. So that gives me my 17 out of 17, which is 100%. Okay, very good. Now the next question just says find those relative frequencies. Okay, we already did. Find those. I already just went ahead and included that in the table. Find those relative frequencies because that's our percentage. Now, here is the big main point for this section. Determining if having a particular political view is independent of what gender you are. And what that would mean is this. If having a particular view is not affected by what gender you are, then these conditional percentages would be the same. If being political, or about the same, roughly the same. If the political view would be about the same for men as it is for women, then that meant it was equally distributed amongst all of you, and it did not matter which gender you were. But as we can see here, is there a difference, a significant difference in the distribution of the males' political views as opposed to the females? Okay. Then political view and gender are not independent of each other. One depends on the other. So what I would have to say is that, if you are a female, you are more likely to be liberal or conservative. If I said, okay, I got a female here from my first period class, then they're more likely to be a liberal or a conservative. Whereas if I said, I got a male from my first period class, probably going to be a moderate there. Okay, so I would make a statement here, and I would say, the question is, are gender and political views independent? And I would say no. You are more likely to have a particular view, to have a certain political view due to gender. Okay, another way you could say that, your political view depends on your gender. I don't know if I would definitely make that type of relationship of saying that dependent, but they are certainly not independent of one another. Okay? Questions there? If you looked at the last question that said, are gender and political view independent? Oh, yes. Okay. The question here is, how did we do this? What's the conditional relative frequency distribution of gender among conservatives? So, of gender, so I was getting, you know, of their gender was on the bottom. So, out of males, what were the conservatives? Okay, so let's do that. Of males, what was the conservatives? 0, okay. Okay, so of females, what was the conservatives? 5 out of 17, okay, which is our 29.4%. Okay, it's kind of that of gender, that means that's your total that you're getting it out of. And then we were finding the conservatives out of the particular genders. You're finding a percentage. And yes, you're finding a percentage and you're doing it of a ratio. Okay. All right. Thank you. Very good. Next, this graph that you have is to demonstrate to you that a bar graph is an easy way to, a segmented bar graph is an easy way to tell independence at a glance. Because if these bars were all the same, for male we had no liberals, we had 100% moderate, and we had no conservatives. Whereas with our females, what was our thing? We had like a little bit of liberals, mostly moderates, but we did have some conservatives. If they were independent, if political view and gender were independent of each other, those bar graphs would look pretty close to each other. Do those bar graphs look alike? No. So since those bar graphs don't look alike, then gender and political preference are not independent of each other. They are intertwined. Why do they look different? This is because we had 100% of our males were moderate, and this is our females. We had a little bit of the percentage that were liberals. Because I'm making a total, a segmented bar graph, takes the total 100% females and it segments it into the types that it's made out of. So this is the segment that's liberal, and this is the segment that were moderate, and this is the segment of the females that were conservative, totaling up to a full 100%. Okay? And why is my moderate here on the females look bigger than the conservatives? Because, yeah, we had a higher percentage on our previous data. Okay, very good. So that's the end of the marginal and conditional distribution discussion. Now we have 2 more topics. The next topic is this down here, the area principle. There is a really good sample in your book. So when you read chapter 3, make sure that you are looking at, there's a graph, and it's got these boats, and it shows you the Titanic boats, and it does it by class. So read the Titanic area principle. It was a good example. Okay. All right, but here, let's take a look at this one. This graph on the left is very pretty, but it violates the area principle, which states that you want your areas to represent the appropriate value and relative frequency of your amount that's happening. When they tilted this graph left and made it all pretty and 3D and everything, this pink actually has a visual skew to where it's smaller than the actual pink amount that it should be. Okay? And so that's dangerous when you try to make a graph and go into the prettiness factor or whatever. You need to make sure that you maintain equal areas for the classes that they are supposed to be representative of. Another example is this one down here. What's wrong with this graph down here? Yeah, hello, look at the 50%. We would expect, because it's on a 3D and it's kind of spent, it looks twisted, you know, and that doesn't look like a full 50%. So we would expect that 50% to be full down like that. Okay, but anyway, because of the viewpoint that they did, the problem is that the 50% doesn't look like half. What? Oh, okay, good. Good point. The other problem is that those it all doesn't add up to 100%, right? Okay, good. So there's two problems. Doesn't all add up to 100%. Okay, good. So two problems there with that chart. But the area principle was involved. All right. The final discussion is on Simpsons Paradox. And I actually prefer the website or the summer articles example on Simpsons Paradox than this one that's given to you. Therefore, we're going to get out of this, and you're not going to actually write notes. You're just going to kind of follow along in this Simpsons Paradox discussion here. So let's go to the summer articles, Simpsons Paradox discussion. All right. And in fact, on your summer articles quiz, I had put these 4 charts into your graph, and I asked you a question about, or into your quiz, and I asked you a question about. But let's go ahead and go through these. Okay, you ready? All right. We're talking about students that took high school physics. Okay? So think about yourself. Are you taking high school physics, and why did you take high school physics? If you took it, why would you take it? Oh, it was required, really? Okay. Not AP, but A physics. Okay. So it's required here, but why would you perhaps maybe, let's do that, let's talk AP physics. Why would you go extra and take AP physics? Even if you didn't get college credit, would you expect that then when you took physics in college, you would perform better? Okay. So that's what we're showing here. These are students that went into an engineering program and went into an engineering-based or a calculus-based physics, okay, as opposed to students that went into a liberal arts program at college. Liberal arts, you know, English, more, you're geared towards more English or fine arts or not as science-like. Okay? Do you think that the physics would be as rigorous in a liberal arts program as it would be in a calculus-based engineering program? Which do you think, which physics college course would be more difficult? Okay, so this is more difficult. All right, so now that we have that fact underway, let's look at these graphs. 50 high school students took physics in this, that took college engineering physics, and they averaged an 80. Okay? 5 students went into the engineering program and had not previously taken physics in high school, and so they made a 70. So they had some grants. So were they better off because they took high school physics? Yes. Okay, so it helps to take high school physics. Let's look here. If 5 students, why did only 5 students that went into this liberal arts program take high school physics? Okay, it's not really geared toward it. Good. So they're, you know, they're thinking, hey, I'm just going to be like an English major. I'm not I'm not doing this physics thing, you know, because some people that are strong in English aren't keen on the math. So, but those 5 that did take high school physics, man, they hit that liberal arts base, you know, that liberal arts physics out of the park. They got a 95. 50 of them did not. They still did pretty okay. They got an 85. So would you have to say that still, indeed, the students that took a high school physics course did better in their physics class in college? Would you say that statement? Okay. So I'm going to say those who took high school physics did better in college physics. Okay, so we've established that main point from this. Now I have to erase that. I did all of that. Now I have to erase it. I was thinking I could keep that on there, but it's a website, so it's not going to. So now let's go and talk about these last 2 charts. Okay, so we established from those individual ones. Okay, this combines data together into a different type chart. So here they combined together the engineering students and the liberal students and said, okay, these are the students that took high school physics. Look, here's their average grade in physics, college physics. Look, that averages out to an 81. What do you have to kind of say about that? The majority of these students in this upper graph were what kind of students? Okay, good. The majority of these students were engineering students. Therefore, they took the harder physics. Therefore, the average grade was 81.4. Whereas down here, what's the majority of these students? These people did not take high school physics. The majority of them were going to go into liberal arts. And look, they did fine. What's their overall grade? Higher than that. These people took high school physics. These people did not take high school physics. Not take high school physics. And what does it appear as though happened? Those that didn't take high school physics actually did better. Why is this happening? Because this is a bigger chunk of liberal arts-based physics, which was easier, higher grades, so that became higher. This was a heavier in calculus-based physics, engineering program, so it was lower grades because it's just overall harder, so this was overall lower, even though they took high school physics. So according to this, if you were just looking at that data, you could skew it and say, well, you shouldn't take physics in high school. Look, it's going to mess up your brain. You will do much better if you do not take high school physics. You will get a higher grade on your college physics class. Are you following the problem with that? Okay. So Simpsons Paradox says that when you combine these 2 data sets together, it skewed the data and made it appear as though it was represented in a much different way. It kind of hid some of those lurking variables, didn't it? Kind of took away the understanding of those lurking variables as opposed to these other 2 up here. All right, so that's what Simpsons Paradox is about. So you make sure that, and I'll go ahead and put this back on here again, that you have skimmed through Chapter 2. You've skimmed through Chapter 2, your assignment, and you don't have to do that fully. I would just kind of go to the homework problems, and if I have to go back and look at the reading, I will. But I definitely want you to read this. This has really good examples on the Titanic. It takes you through all of them. I really like the Titanic examples. Definitely read this chapter before doing these problems. Okay? That's it. So you guys can work on that for the rest